So the next thing we want to discuss are stationary states. So the idea of stationary states in quantum mechanics was introduced by Niels Bohr. When he said that the atom, the electrons around the atom, had well-defined orbits, but these orbits, unlike in classical physics, were not radiating, and therefore their energies were stationary. So the idea of stationary state has more to do with waves than particles. For example, we are familiar with stationary states of a vibrating string. So let's take a vibrating string. So what happens in a vibrating string is that every point on the string has some amplitude, and given its amplitude in time, it vibrates. It performs simple harmonic motion. So if you were to write the displacement of such a string, it would be some function phi, and it would be a function of x and t, and then the amplitude would be some function of x, so x goes in that way. Then this is phi. So this would be some function of x, and then there would be some time-dependent factor, which would be given by, say, sine or cosine omega t. So this is what we expect for classical stationary states. So what would be the quantum analog of that? The quantum analog of that would be something which has some well-defined energy. And so the quantum analog would be some wave function x psi, and we take our system to be one-dimensional, and this will have a spatial dependence, which is small psi times x e to the power minus I omega t. So this would be the quantum analog of what we would call a stationary state. So if we now insert this into our Schrodinger equation, then what do we get? So let's write the Schrodinger equation. It's I h bar partial derivative of the total wave function with respect to time equal to minus h bar squared by 2m, and then we are in one dimension now, so it's del squared by psi del x squared plus a potential term and psi. So now if I introduce this factor into this equation, from the first term I get what will happen is that the time derivative acting on this guy will bring down a factor of minus I omega. This minus I and this plus I will give me plus 1. So I get h bar, and then I get omega, and then I get e to the power minus I omega t times psi. This is small psi. And the first term on the right-hand side, we get minus h squared by 2m. And now this spatial derivative only acts on this guy. So what we get is that the exponential factor just comes out. And then the partial derivative becomes a total derivative because psi, this psi only depends on x, so there's no need for partial derivative. And then we have v times e to the power minus I omega t times psi. So now there is going to be some cancellations. So there will be a cancellation like that. And therefore, what we will have left is an equation where we have energy, so I'm replacing this by E, times psi is going to be given by minus h bar squared by 2m, the second derivative of psi, and then the potential energy like this. So this is the Schrodinger equation for stationary states. So this is the, or it is also, as it's also known, the time independent Schrodinger equation. And what it does is that it gives me solutions which have definite energy. In the business, these solutions will be called energy eigenstates, and we will talk about that later in the course sometime. So the total solution of the Schrodinger equation would then be given by xt, and then whatever solution we get from this equation times the e to the power minus I omega t. Now, a very special case of this is going to be the free particle, and we saw that the free particle was given by this thing, e to the power minus or e to the power plus I kx minus omega t. So this was represented a wave moving to the right. So in this wave function, the spatial part psi of x would be given by e to the power kx, and the energy part is e to the power minus omega t. So this is a special case of stationary waves, stationary states. And in the next section, we'll see more complicated forms of stationary states.